We are discussing the Markov modeling facility within MS4Me, and so far I've considered the evaluation of cost effectiveness of healthcare interventions, uh, where we discussed both the continuous time model and the Markov matrix simplification that's automatically generated from the more complex model. And today we're going to consider now more about the complex model and what kinds of questions it can address that are not covered um, by the more simplified model. After creating the sick patient CTM model, we can find the DNL version of it, Dev's natural language, within the model.dnl folder, and we can click on it to bring it up within the view of the editor. And we can then edit or interact with the state designer as whichever is more comfortable to enhance it for further qualities. So one thing we want to do is add some output ports, so we generate output on very sick time and lifetime to provide outputs from the model for those two times. And we also add some access to the transition information available from the XML file that has the transitions probabilities in this manner. And here we're going to use the name of the model to set values for the probability of getting very sick, going from sick to very sick. So the name contains susceptible. We'll set the probability to 0.6. If it's very susceptible, we'll set it to 0.9. And if the name contains immune, we'll set the probability to 0.1. We can have other parameters of this nature so that we have multiple attributes that can determine the transition probabilities within a model, and in this way specialize the model for different patient characteristics. We can output the values of the probability of being very sick on the port very sick time, and we can output the lifetime, which is the time until the model goes into the dead state on the port lifetime. Also, we can select from the graphics that are available that are generated from the menu. If we only want to show, for example, the probability of being very sick, we can comment out the other ones and just leave that one, and then we will see when there's multiple instances of the model, we'll see distributions and plots of this particular probability. Having developed a model of a sick patient that can be specialized to have various characteristics that relate to its transition probabilities, we wish to embed that description as an instance within a larger model containing copies of that model as well as other components We can use the system entity structure to do that, and that structure can be generated within the models.scs folder, and when we generate that, we can observe it within the editor or within the sequence designer. Here we have the sick patients made up of a sick group and an experimental frame for capturing the times generated by the instances of the model. And this is the way in which we express that we have more than one copy, and we're going to index the instances by an ID, and also we're going to allow the instances to be specialized by a specialization called susceptibility, which has values immune, susceptible, or very susceptible. And we could have others of these kind of specializations, and we could further enhance the system entity structure. But the way the components are coupled can be specified by the coupling, and here we're saying that all the instances of the sick patient model send the output very sick time to the experimental frame, as well as sending the output lifetime to the experimental frame. And this view, the outline of the system entity structure, gives a visual representation directly available of that information that we just were displaying. We now wish to run the sick patients model with a number of sick patients and a variety of characteristics. To do that, we go to the pruned entity structure and create a file in which we restructure the system entity structure so that we get a definite number of instances. And to set the number, we use this instruction here, for example, as 5, so that we can rapidly generate that example here. To generate the example, we run that pruned entity structure in the sim viewer, and then the result is a model, which is a Java file, and we can run that file in the usual way. The sim viewer opens up and displays the model and its 5 components, and the distribution in this case of 2 susceptible and 3 immune versions that were generated at random because we didn't specify the actual selection in the pruned entity structure. We notice that there's a outline as well on the side, and that will display the model components and their changes in state as the simulation proceeds. And we hit the view button to make that happen. And we notice the messages flowing out from the components carrying the outputs that we specified, which we can view using the ports. And we can also watch the changes in state as they change in time steps, which are varying according to the next events that are occurring. If we hit the run button, then the model will run as fast as it can, and we can watch it display the probabilities of being very sick for the different patients as time proceeds. And we notice there's quite a difference in these probabilities because of the randomness of selection with the different characteristics of immune or susceptible. The experimental frame generates distributions every so often as we can set that period. And for example, here we have after 100 time units the lifetime histogram, which shows two deaths that have occurred in their times, and the distribution of very sick probabilities, which we can see here, varies from 0.75 to 0.2. Let's summarize to review what the MS4Me Markov modeling facility supports. Cohort models follow patients as a group over time in aggregated form. They are easier to develop and calibrate. They run very fast, but they cannot accommodate patient differences. Individual models can accommodate individual patients' stochastic disease and treatment trajectories, but they require more detailed data and are much slower to execute and require numerous runs to achieve statistical validity. The MS4Me Markov modeling facility allows both approaches to be used in an integrated manner. The Markov matrix supports cohort-level models where aggregations of homogeneous patients can be tracked. Embedding the CTM or continuous time models within multi-aspects, as we've seen in the system entity structure, enables them to serve within patient models to produce individualized stochastic and disease trajectories. To learn more, go to the MS4 Systems website or send email to support@ms4systems.com.